Welcome to this video on Huffman coding. Huffman coding is a compression method that makes files smaller. It's a form of lossless compression, and that means that when you put the data into the compressed file, you don't lose any data whatsoever. We're going to see how Huffman coding works. So here we go. Huffman coding depends on one thing. When you have a data file, some bits of data are going to occur more often than others. Most often this is in terms of text, and you can see I've got some Scrabble letters here, and the letter A occurs rather a lot, the letter E even more, and the letter Z and a few others occur very few times. Now when we use ASCII, what we find is that we use 8 bits for every character. So that means we use the same number of bits for an E, which occurs all the time, as we do for a Z, which occurs, well, hardly ever. Huffman coding is different. Huffman coding means that we use short sequences for the common letters and longer sequences for everything else. So, let's have a look. We've got 4 stages. First of all, we need to find out what occurs most frequently. Now, we could just use the English language, but actually we've got all sorts of punctuation, symbols, this kind of thing, which we need to know how often it occurs. When we have some kinds of file, like for example an HTML file, you're going to get lots of angled brackets. That's going to be a very, very common thing, and so it's going to have a short code. When you compress a story, not so many angled brackets. So what we do to find that out is we generate a frequency table. Then, after that, we construct a thing called a Huffman tree. We will get to that. The Huffman tree then gives us the binary codes for our Huffman table. And once we've got the table, we can use the table of binary codes to encode the text. Each stage isn't that complex. Perhaps the most complex is constructing the tree, but as long as we follow the rules, it will work out just fine every single time. So we're going to use this really simple text, red lorry, yellow lorry. And we're going to include all the characters, not just the letters, but spaces, punctuation, this kind of thing. And we are going to do that in a table. So all I'm doing here, really simply, counting up the number of R's, and I just write the number is 5 in there. There are 2 E's, there is just the 1 D, 3 spaces, 4 L's, 3 O's, 3 Y's, 1 comma, and 1 W. That's all it is. On the next slide, we're going to see this table again, but I'm going to put it in order of frequency. So we have the least frequency at the top, and the frequencies are going to go up. And the reason for that is it helps us to construct the Huffman tree accurately. So I've got my table over on the left, and I've got these ascending frequencies. Now, when we draw a tree like this. These things are called leaf nodes. And then there are internal nodes like this, another leaf node, an internal node, and that goes all the way up to a thing called the root node, which is the one at the top. So we're going to draw this into a tree, and all of the letters are going to be leaf nodes, and they're going to have a frequency attached to them. So we're going to start off right at the top of this table. We're going to consider this one first and also this one. So I'm going to write those onto my diagram. So I'm going to have D and a comma at the bottom. And each of those, as you can see, have got a frequency of 1. So I'm going to write a little 1 there and a little 1 there. And I'm going to join these together. 1 plus 1 is, of course, 2. Now, these are dealt with, so I can cross them off my list. And we are now going to add some more. Now, when we're looking at this, what we need to do is we need to consider both what's in the list here and also what is on the tree. So this one, for example, is an available node. I can see that I've got a 1 here in my frequency table, and I've got an available 2 here in my tree. And I've also got an available 2 here. When we're doing Huffman coding, we always prefer what is in the tree. So we're going to join the W onto this. So I'm going to say W here, which has a weight of 1, and I'm going to join it to the 2. So that forms 3, and I can cross out my W. Now we've got the same situation again. We've got an E here, which has a weight of 2. There is a 3, but we want to prefer the 3 on the tree already. So I'm going to add in another leaf node, an E, and I'm going to add in the weight of the E, which is 2. I join those together, and of course 2 plus 3 is 5, and I can cross out the E. Now we get to this next situation, and yes, there is a 5 in the tree, but we've got 2 lower values here, 3 and 3. So I'm going to put those over here. I'm going to say space and O. And I'm going to join those together. Space is 3, O is 3, so that's a total of 6. My next 2 values here are 3 and 4. Both of those are lower than the tree. So again, I'm going to put in over here Y, which is 3, and L, which is 4. I join them together to make 7, and I can cross that out. And lastly, I've got R over here, which is 5. The lowest of these 3 values I've got available in the tree is 5. So I'm going to put 5 in for R, and I'm going to join that together to make 10. The lowest 2 values in the tree now are 6 and 7. They come together to make 13. And then I join the top of the tree, 23. As you can see, everything is joined onto the tree now, so I know my Huffman tree is finished. If you want to try a Huffman tree of your own, then there is a link down at the bottom of this page, just here, and if you go to that site, it will generate a Huffman tree for you. So you'll be able to check whether you've structured it correctly. Now that I've made my Huffman tree, I can start to generate the codes. On the next slide, you'll see a more formal version of the tree, just made it look a little bit neater for the next stage. So here we are. All I need to do to start this is I label left as 0 and rights as 1. 0, 1, all the way down, just like this. And then I bring in a table to put in my codes. So to find the code for space, I find space on the leaf node here. And I can follow it down from the root node. So I go 1, 0, 1, and write that in there, 101. Okay. So now let's find the comma. Now the comma is all the way down here. So to get to that, I go 0, 1, 1, 1, 1. 0, 1, 1, 1, 1. And I'm going to do the last one, which is D, which is all the way down here. So I go 0, 1, 1, 1, 0. And you can fill out the rest of this table. I'll leave that as an exercise for you to do. If you want to, pause the video, give it a go, and then on the next slide I'll reveal the entire code. Here it is. Here are all the codes, and to encode my string, all I have to do is I look at the first letter, R, and I find it in the table. And R is 00. There we are. Then I find E, and E is 0, 1, 0. And then D, 0, 1, 1, 1, 0. Now you don't have to put any spaces in between these codes, it's perfectly fine. If you notice, for example, the code 0, 0 here, if you start off and you've got 2 zeros in a row, no other code has 2 zeros in a row. And so you know it must be this one. That then stops and you know you're looking for the next letter. Again, carry on writing out this code and I'll reveal it on the next slide. The last thing is, just to make my life slightly easier, I have sorted this and I've sorted it A to Z. That means I can find my characters a bit easier when I write this out. So lastly, here we are. This here is the original ASCII. It takes 192 bits because there's 24 characters and each one takes 8 bits. Huffman coding, we can do the whole lot in 69 bits, so you've saved about 16 bytes. So if you get this in GCSE questions, then if it asks for the space saving in bits, you can just give the raw number in bits. So you calculate the difference between the two. If it asks for it in bytes, then what you need to do is divide that by 8 and round down. Last thing, what I just told you, it's not quite right, okay? Because as well as transmitting the Huffman code here, we also need to transmit this table in order for the person receiving the message to decode it. Remember, the table is different for every single message, so if we don't transmit it, they've got no chance of understanding what you mean. Second thing is, you'll notice how none of these codes are anything like 8 bits long. That's because we've got relatively few characters. And so most of the space saving that we've had is actually due to the fact that we've got relatively few characters. We could just use a 4-bit code to represent these characters and we'd save a whole bunch of space anyway. But if you imagine a book, it's going to have a huge number of characters in it. It's going to have all the letters, capitals, lowercase. It's going to have a whole variety of punctuation, maybe some numbers as well. And so obviously it's slightly different. And the second thing about a book is it's longer. So when you encode something like, for example, A Christmas Carol, if you encode the first chapter, the size of the Huffman table isn't really going to be any bigger than if you encode the whole book. So your saving gets better over time. Last exercise. We just generated a Huffman tree. So if you have a look at the table, I haven't changed the table, you should be able to decode this message over here, and you should be able to tell which planet I am talking about. Give it a go. I hope the video has made Huffman coding a little bit clearer for you. If not, you can always ask questions in the comments. Thank you for listening.